it wasn't hard, it was just annoying. So like, you have to like read, you have to write papers, you have to do stuff like that.
Usually, you just go to a different the 16. That's what 461.
All right, guys, let's get the lecture started. Thank you for coming to the lecture today. So little disclaimer. I just got out of a 4-hour continuous PC meeting discussions. So if today I see a little bit slow, it's because my brain is a little bit fried right now. Please bear with me. But any question you had during the lectures, please just feel free to raise your hand and ask me. So today we're going to talk about 2-chains and the application binary interface, or ABI. Before we go to the lecture content, let's some quick announcement. Homework 1 is due tomorrow. Exciting times. Probably like 30% of you guys haven't started. So after this class will be the good time to start. And we have a late deadline on Saturday. If you're willing to take 10% of your grades off, you can also, choose a 24-hour window. Not recommended, but you're all adults. And for next week, we will inform that next Monday is a holiday. Is that correct? So for folks in the lab session on Monday, next Monday, you will be actually doing that in the Monday after that. So you started with the first lab of the class. Now you became the last lab in the class. Sorry about that. And we have the last expo, so basically the big demo day, set currently to be Tuesday, April 22nd, last day of the class. It's most likely going to be at the EECS building in the atrium, like the big common area, so that not only us, but everyone or your friends and roommates, whoever they want to check out your cool work, they can come and you demo to them. It's a very good skills to have, on top of course, like the technical skills to build the system, but it's almost as important to have the communication or like the ability to present your work, to show why is it important and how they work nicely with either existing systems or how they enable new applications or new sets of design spaces, etc. So, yeah. Okay, so again, today the components of the day is going to be batteries. Batteries are quite hip right now because of the EV stuff. You probably know or not knowing, like most of the EV used to recharge batteries are actually quite similar to some of the batteries you will be using in our class or in like other embedded system applications in terms of the materials. So generally, they are different materials used for these batteries. Two commonly used ones you likely encountered in our class is the nickel metal, and the Leo iron or Leopold. If start with Leo, that basically means they have the Leo in them, and that's a lot of the batteries that's being used in EV nowadays. So, and that one is the one that's less safe to be working with, or you have to put like more cautious into this. For the left side, it's pretty much the this one. So basically, that's the dry batteries you use, like AA's, AAA's. If you look at the curve here, this curve basically means the amount of voltage it can hold against the amount of current that's being drawn at a given time. So you will see that the curve is actually pretty steady in most of the time until it, of course, runs out of the battery. And on the right side, which is the lithium-ion battery, the curve is much more various. So it's not that regulated. So if you're using any of those batteries for your project, make sure the peak, to make sure that you double check on what's the voltage range that's being used for that component, and make sure not just the voltage level mentioned on the front, but also check the data sheet of that lithium battery to make sure the high voltage where it started does not exceed whatever your component is. I think most of the time, like the digital components you guys gonna be interact with have some sort of like current or like voltage protection. Some of them even have like some regulators on them, so you should be fine. But just in case, always double check if you're using one of the lithium batteries. Yes, and you will have different looks of batteries. So you should always keep in mind that do not solder a battery. It's usually because that they don't really handle well with the heat. And then if you are not like super experienced with desoldering iron, you can a lot of time overheat the battery, either through the wires connected to it or just by like accidentally touching. So do not do that. And whenever you're adding a new connector to the battery, always double check if it's either short-circuited or is it in the correct connecting, the positive goes to positive, negative goes to negative. And they are different, I guess, appearing, like the looks of the batteries. On the left ones, that's pretty much, if you're working with something like this, it's pretty much means like it's a, so to speak, like bare batteries. Not much of the digital control components are put on them. So for these ones, make sure you know what you're doing, and then the current or voltage that's outputting is going to be not very stable. As opposed to like on the right side, those things you will see like a little small chips on them. They are generally like have some current protection, over current protection, or some voltage protections. So it would be able to disconnect itself if it exceeds some amount of current that's been drawing from the, so prevent you burn something or destroy some of the components. Yeah, so try to avoid these, and definitely do not solder on those two tips. Yeah, a little bit of recap from the last lecture. Last lecture, we look at the background of the ARM, and then we look at the ARM v7m instructions set architecture, ISAs, register instructions, and some of the memory manipulation examples, which I think we actually went too fast at the end, and I have the impression that especially the group exercise always like went way too fast. People are probably a little bit tired, and so let's actually go through that one more time, and then we'll go through together instead of working in groups. And you can feel free to shout out answers whenever you have it. So, does that sound okay with you guys? Cool. Let me actually go to a more easier. Okay, so let's look at them together and fill it out. I'll just give you some very useful hints. 152 equals the hex 98. So what's this one gonna do? How are we gonna fill it out for you? It basically give you the value here to be, yes. So can anyone tell me what this function does? Just shout out answers if you know them. Oh, I should probably give you some time to read the question as well. Yes?
Register 0 and register 1.
And so what's the value going to be in the register 1 in this case? Oh, sorry, can you say one more time?
It should just be the hex number that can register 0.
Okay. Think one more time. Any other? Yes. And that will be the 64, right? That is correct. Yeah. Or make sure that it's using that as the memory address instead of the direct value because we have the bracket around it. And usually when you see like load or store, it usually means interactions with the memory. And then when you see like move or add, these type of things, that's the interactions usually between the registers. So just something to keep in mind. So, okay, great. Now that we have this in the register 1. Okay, let's go to the loop. So what's this one going to do? Any guesses? And just a little quick recap. This summary chart is like super useful. You know, we have the no index and the pre-index with update, as in like immediate, as well as the post index. You see those are load, but you know, they works the same way as store. So yes.
Yeah, is it gonna load the contents of R1 in the memory location that R0?
Sorry, this is the store. So the actual component, yeah, it's a store.
But yeah, it'll store the contents of R1 into the memory location that R0 points to, and then increment the contents of R0 by 2.
That is correct. So which exactly memory are we talking here?
So I think 0x98.
Here, right?
Yeah.
And then we replace that with?
The content of R1 is 0x64, which I guess won't do anything, but.
Yes, it basically overrides that value to the same value, right? Okay, perfect. And then there's 2 added to the R1. So that R1 became, sorry, R0, my bad.
Yeah, so it becomes 0x98.
That is correct. Okay, so what happened here then? Which part? This one? Yeah, so the value in the R1 gets stored into the address of the R0. And then we added 2 to the whatever value inside of the R0 after this process. Is that clear with everyone? Okay, perfect. So what's the next one does? The store R1 and then a immediate add on the R0. Okay, I will let other people answer that one. Yes.
So that would store the contents of R1 into 0x96 because we have to use the contents of R0.
I see. And then at the end of this, okay, so which happens first? Does it happens to the R0 first or happen to the store first?
So we add 2 to the whatever is in R0 first.
So this one became the C. Okay.
And we store 0x64 in that location. 0x.
I'm going to just save all the zeros, you know. Imagine there are a bunch of zeros there. That is correct, yes. So any questions on that one so far? That's all sound good? We add first to the register value, and then that kind of updates what's the address in the memory that we're going to store the R1 register value into. So that became the 9C instead of the previous 9A. And, oh God. Okay. So what's this one going to do then? Okay, no. Anyone else? Anyone who haven't answered yet? Okay, yes.
Return the address to store the value register 1 and 2. Calculate that by adding the value 4 to the value of register 0 times 8. So the address is stored into 0x8, and so we store the content of register 1.
So the 6, 4 stored here, right? And what happened to the register values? Yes, but like what happens here? That is correct. So when we have this bracket without the pound sign, it adds the value to the address immediately to where you're going to store them, but then that operation does not update what's the value inside of the register. So after this instructions in the R0, it's still 9C, but the content of the R1 got stored into the A0. Is that clear to everyone? Any questions? Okay. So what happened here? Yes.
Contents of R1 will be increased by 4.
So it became
Yeah,
6. Yep, perfect. And then again here, we're going to add 4 to the register 0 as well. So this one actually became the A0. So this is the cycle 1. Is this cycle 1 clear to everyone after this? And then we go back to the starting here. And what's that going to do again? Let's just do 1, 2 cycles and then make sure everyone understands. And then if you already answered before, do not answer this time. Give other folks some. Anyone? When we go back to the, oh, by the way, this is B basically stands for branch, and it branched back to the other label, which is the jump. Come on, I know you guys know the answer. Yes?
So write the contents of R1 to the address from R0, and then afterwards increment R0 by 2.
So it's going to be go to which one exactly?
Here.
A0, and then put value. Yes, that's correct. And then we update here, right, to A2. Okay, and this one. Yes?
It means like R1 is like memory, it's like the memory of R0 plus 4, and then R0 is R0 plus 2. Oh, sorry, I think
So this becomes A4, right?
Yeah.
And then the value stored into
R0 is included. Oh, sorry, what's in the memory that's inside of R0 is also included by 2.
and then the register 1 value got stored at this location, right? Okay, that is correct. And then, next one's similar after that. It's basically we add 4 to this value, but without updating it. And then we store the value inside of the register 1 to that location, which is here. And then we do not, update the value here. And then the next 2 is just add to both of the register, and then do the loop one more time. Does that is that clear to everyone? Or anyone still have any questions about the memory? Okay, perfect. Cool. You're gonna have a lot of fun in the exam later. All right. Yeah, so, incredibly useful tables here, as well as the answer. It's basically just keep doing that, it updates at the current address, and then write 2 right values, and then add 4, and then do that like always. Okay, cool. Let's get that out of the way. And then in today's new content, we're going to do basically 2 parts. First is the assembly program and toolchain, and specifically we're going to use like the GNU, or we should call it GNU toolchain. And then we're going to talk about the directives and labels that's inside of these toolchain. And we're going to give you a couple examples. And then the next part is going to be talking about ABI, the application binary interfaces. So essentially like a set of rules that defines how the software interact at the binary level with on like a specific platform. We're going to specifically talk about how these bunch of subroutines, or like how when they call functions, how the registers are going to handle all the branches where all these data from the previous functions got stored into and how they handle the conflicts between different functions within the temp program. Okay. So a quick introduction on like the level of the program codes. So on the top we have like the C program, which is like a high level language. I think in most content you will think C is like pretty much low level program, but in our courses in this lecture it's going to be the highest level you interact with. So basically you wrote the language, you wrote the logics, and then it got compiled into the assembly language. And then there's a thing called assembler that actually assemble these assembly language into machine codes, basically 0 and 1s, binaries. And during that process, during like these process, they're gonna figure out basically where to put those things in the memories and how to basically plan. They call like floor planning, basically how to plan the memories and registers and stuff to make sure it works. And this is the IDEs, like one example of the IDEs. Basically, these are most of you guys are going to be interact with. You wrote the programs inside of the IDE, and most of the previous process is hidden from you. And so, good for you. And just by interacting with like some GUI-based IDEs, we're able to do a lot of interactions without knowing it to the lower level of the hardware's memories, etc. So how does it work? In fact, there are a bunch of like ARM development tools exist that help you handle from the high-level language, program language, to the lower level mapping or planning. And you will notice that a lot of them have what they call like GNU, or GCC in them. So basically, it's a open source set of tools that for making computer works, especially, particularly in our case, for the MCUs, microcontrollers. So GNU project, it's initialized by this free software initiative. It's actually called Free Software Initiative, launched in 1983 by a man called Richard Stallman, or IMS. He is quite a character. He actually based at MIT. He sits one floor above me when I was there doing my PhD. And yeah, he is very, very characteristic. And then basically all in for the free program. Every time anyone sends like a department email with like a Google link inside, he will reply to the entire department saying that you should not use Google Form or Google Doc because some of us might not be able to ethically open them because it's not free. And then he got busted during one of the abstain discussion in the department. But that was, yeah, anyway. So what I'm saying is a lot of people worked very hard for free and then create all those tools so that we guys can just interact with all those hardwares by writing some high-level codes. So I think they deserve some of our respect in this case. Yes, so the ones we're gonna particularly be interacting with is the GNU ARM embedded toolchain. So it's a collection of tools that's specifically designed for developing software for ARM-based embedded systems. It's like a subset of the GNU toolchain that we briefly talked before. You have like compilers that put the C code, etc., to assembly or directly to object. It has the binary util for creating and managing the binary programs. It has like libraries, etc. And a bunch of also debuggers and some libraries handler. You don't have to know too much about the bottom tools. So yeah, today we're gonna mainly talk about like the compilers. And this is just basically an overview of how this toolchain generally works. It takes C files, some assembly files, and then some library files that you imported, and then they got to the GCC compiler. Uses like the thinker script, or sometimes it's called makefile, and then all those files became into one executable files that the machine actually can run on. And this is like an example of the assembly program. And on the top, these things are called directives, and it's basically it's like a help functions that tells the assemblers what to do. Like for this one particularly, it has with the global stars, etc. It basically tell them that these are the public variables, and then they have also like labels, and then the core code, which we'll go through one by one in the next few slides. So yeah, first the directives. Like I said, global exposed variables, and then the load here, the dot byte here actually means a little bit down there. It actually means load the variable into a labeled data. So essentially, it just puts whatever that's here. Can you see my cursor moving? Okay. So basically, just put whatever these values into the memory. Where exactly it puts into, we don't have to care too much. The assembler is going to figure that out and then make sure it's being labeled properly. But this is essentially what it does. Yes. Yeah, directives are special instructions for the command in assembly language. And then the ones we mentioned, the dot byte is here, and there's also some other examples. For example, the fill is basically fill the whatever that's pointed to with zeros. When you're trying to initialize something, or you're trying to clear out something, or just you want to have like a whole 32-bit, but then you're also only using 16-bit of it. You want to fill it with zeros. All these sort of things that's being handled like at a very low level by the for providing information for the assemblers to figure out in the binary level. And there are a bunch of like moves, and then in case you guys don't remember, the normal move is basically copies a value from a register to a designation registers, or like a brand new value into a register. Both are the same thing. And this is a quick, like a very vanilla version of the move. We also have some fancier move. This is move W or move white. It writes the 16-bit value into a register and clear out into the lower 16-bit, and then clear out the upper 16-bit. And then working together with it, there is a move T or move top. Basically, it fills the top half of that register, the top 16-bit, and leaving the lower 16-bit unused. So these things basically allow you to import or write larger data into the register, because the register are 32-bit, right? And then the instruction set we have are either 32-bit or 16-bit. It's a hybrid that we used in Thumb 2. And even for the 32-bit instructions, the amount of bits that's saved for actual data is only 16-bit. So if you want to load something 32-bit into a register, you're basically going to do the move wide and then move top. Make sure you do the move wide first and then move top, because the move wide will clear out the top 16-bit. Okay. And there's a bunch of other directives. It basically told the programs, or told the assemblers to, these going to be load the lower 16-bit of the data meaning whatever we put up there in the dot byte, so or whatever the data is currently pointing to, and then only take part of that data. Remember, like all the instructions or all the data comes in 32-bit. So in this case, it basically take the lower 16 and the next put the upper 16 to the top of the register. Yeah, exactly what this says. And yeah, basically with these prefix, you're able to get half of the 32-bit constants from the data. Yes?
What is the order of execution of the code?
The order of the execution, you mean these? It's just the top to bottom. Yeah. And then you're gonna put in terms of the move specifically, make sure you put the move wide first and then move top.
So the 4 lines are defined as load.
Which one?
What is the point of having load?
This one? The directives?
Yeah.
Uh,
The purpose of this.
The purpose of this is we're trying to load a 32-bit data inside of a 32-bit register. But all the instructions we have can, even for 32-bit instructions, we can at most put 16-bit of that into it. So we have to do it twice so that we are able to put 32-bit of the data inside of the one register.
What is the point of the load and the semicolon?
The load and the semicolon. Oh, yeah, those are labels, basically.
So is it like a function expressive load that is called for line? What is the point of label in the for line?
Wait, is it a question or are you trying to answer the question? Okay, then one sec. So for those are basically, so those are labels, right? Imagine the label, the putting there so that if you're trying to jump around in the, you know where the reference is. Sorry, your question?
Is that the proper syntax for like, could you further explain like lower semicolon like data, colon data?
So the data is basically the reference to the data on the top. So it's not like an arbitrary name. It's kind of referenced. And then these are just the, if I can go to the next slide. So basically these are the upper 16 or lower 16, they are the prefix. So these are already decided, so you know. Good? Okay, sounds good. Any other questions so far? All right. And these are different types of load. These LDRB, it looks very much like load, and it actually means the so load register byte or load register assigned byte. So you can load on like a more byte specific instead of loading the whole thing. You have the ability to do that inside of here. And then, of course, we then have the compare and the branch. In this case, just tell if it's equals to that value. If the value inside of the register 0 is equals to 4, if it is, then it do something. If it isn't, it do other things. Depends on the value of that. It will give you the instructions or like what's the next address of the instructions you're trying to execute. And those addresses are stored with the labels we have, like load, loop, etc. Yeah, this is like a compare immediately, and then if it is, it jumps to a different address. Cool. Is the first part? Is there any questions so far on these assembly examples we have? Just basically how these things works. Yeah.
So how do we know which byte to choose? I mean, there are like 4 digits.
Wait, sorry.
4 byte. I mean, which lower 16 bit?
Which lower 16-bit you would choose?
Yeah.
In this case, it's being stored as. Give you. Yeah, so basically this stores, and then we go Little Indian, and then, can you see this one? So that's what's the value that's being stored. And then we get the lower 16-bit of that, and then to the register 1, just lower 16-bit, and then we got the upper 16-bit to the upper 16-bit of the register 1. Good. The FF means because that's basically -1. That's FF.
So how do we get that?
Sorry, what?
How can we get that number?
How can we? Okay, like where in the memory we know to get that number? Is that what your question? Yeah, so the memory will be assigned by the assemblers. So you don't have to worry, in this case, which memory location exactly it's being stored into. It have the label of the data there, and then you know when you load that data, the program or internally they have their reference to find that data for you. Okay. So, oh yeah, sorry.
What is the purpose of dot space?
The purpose of what? All right. Oh yes, yeah. There's some other directives. I think that means the basically the amount of space you're dealing with inside of this program. Every time you by default increase, like the data take 8 bit, but I will double check on that. But it's one of the directives, and all those what these names means can be found in the manual. Yeah. And then in the exams or like homework, well, especially I guess in the exams, we can hand you like cheat sheet so that you will know exactly what these derivatives are supposed to do or means. All right, let's go to the next fun part, the application binary interface. So or ABI. Essentially, it's the agreement between the programmers on how we're going to structure function calls. And then we're going to imagine you have like same platform you're using, right? It's the same set of registers. And then but you have different programs running on them or different functions running on them. Say the branches that we talked about before, it could be jumped to some of the previous repeated locations to do the execution one more time if we're in a loop, but it can also be something more complicated than that. For example, it branches into a different function, right? And in that function, they're going to use the same set of registers and stuff. So how do we maintain that even when we get back, everything that we needed from the previous functions are still there so that we can keep executing that? So these are some of the ways of doing that. We're going to go through these three main rules. First is like the caller callee save with the registers. And the second is when the calling subroutines or calling functions with the link registers. And then for even more complicated stuff, it's going to be with the stack pointers. So we're using not only the link point register, but also the stack in the memory as well. Okay. Yeah, sorry, I kind of give it away. It's like a contract between programmers on how to share the hardware resources, because there's only limited register spaces. As you probably still remember, we only have 16 registers to work with, and we actually have fewer than that because some of the registers are already saved for specific use cases. So here are some of the basic rules that the ABI has. First, the subroutine or like subfunction must preserve the content of the register R4 to R11, and then the SP as well. SP stands for a stack pointer. So these content have to be preserved before they executing whatever the subroutine that's jumped to. And then there's also the agreement on all the arguments are passed through from at the first 4 registers, R0 to R3. And if we need more for those arguments, we put like a pointer to memory in one of the registers to tell that these bunch of stuff are the arguments, so that we can have more space for that. And then the third rule is that all the return values are placed inside of the R0. And also, or like R0 and R1 if there's more data than 32-bit. And if we even need more space, we basically allocate space on the stack as needed for this purpose, so that all the data are preserved before they enter in the subroutine. And then when they come back, they're able to reload all those content into the register again to keep on doing where they left over. And this is like a quick overview on how the register assignment works. So these four, the bottom four, R0 to R3, basically they're not saved. They're being used to hold arguments, results, or like temporary values. And the callers should not expect them to be preserved in any way. And then we have the parts that the callee must save them before they execute stuff. And then if they have enough space, just put it in a stack, etc. And then there are a couple special ones, like the R9 is one of the special register, and also the R12. They're not super important for our class, this lecture, but just keep in mind that some of these special register has to be also preserved before the callee access the subroutine. Oh, this is the graphics, like a graphics way of showing ways of doing input and output data. So basically, we have on top the arguments got stored inside of the R0 to R3, and then when they came in, there's a bunch of they came in like in a 128-bit arguments altogether. That basically just internally breaks it down. And then after the subroutine or the function calls that happen there, and it will go back to put all the output inside of that same four registers again, and then return that to the previous function. Again, 128 bits. Yes?
On this slide, it says that extra arguments are pushed to the stack, but on the previous slide, it said you attach a pointer to memory. So which one of the two do you use for extra arguments?
That's a very good question. So stack is part of the memory. That's the part of memory location that's, or that part is being designated to store these values. And it basically does a first in, last out fashion. Basically, you push things in and then you pop things out. So they're essentially the same thing, but just this is more specific, so to speak. Any other questions? Yes?
Is the choice of which registers are like the argument registers influenced by our discussion last time about which registers can be used in 16-bit versus 32-bit instructions?
Not necessarily. So these things are purely defined at an even lower level. These these are oftentimes you don't have to worry about these because it's being handled by a proper compiler or assemblers. But this is what's essentially happening, like when how they're trying to assign what to do. These registers are saved for these specific purpose, so that if they happens to have all the registers just enough to handle all those, you have like a small sized code. If it doesn't, if you need more, you have a larger sized program, so to speak. Yeah. And then the toolchain itself, it does a bunch of like optimization as well to optimize for like code size and performance. Cool. All good so far? Nice. And this is what happened for when we're actually calling a subroutine. Basically, we have the the branch here to a specific level, and then specific label, and then the link register or LR there basically holds the return address. Notice that it adds 4 to it because that's storing essentially what's the next executing address of the current function or current routine. So it adds 4 and stored it inside of the link register, and then the PC or the program counter goes to whatever that label address is, so that it knows, what's the address of the instructions of the subroutine that's being pointed to. And any questions on this one so far? Basically, like the LR or link register is kind of like a address holder, so that the program knows where it should go back to after finishing the subroutine. Yes?
Some instructions are 16 bits and some of them are 32 bits.
Uh-huh. That's a very good question. So basically, in reality, everything loads in 4 bytes or 32 bits, and then it basically only stored the address there. And then once it loads back the instructions, it look at specific 5 bits inside of that 32 part, and then figure out if it's a 2 16-bit instructions, or if it's a one piece of 32-bit instruction. Yes.
To sort of just like go deeper into that, like what if you have two 16-bit instructions and the first one says branch? That means the next instruction, once you come back from branching, should be like that same address, like that same 32-bit chunk. Does that mean all branchings are 32-bit instructions, or?
That is a very good point. So there are different ways of handling it. Depends on how the assemblers decide, or like how the compiler decide to handle them. And essentially, you could either do like one of the directives we mentioned before, the fill, basically fill that with all zeros, so that it's make sure whenever the branch is, it's a one-piece instruction. Or it can be like more smart, I guess. It would like whenever it goes to that one piece of the if it detects the first part is the branch, and then it updates the link register to essentially that, but minus something. I think in reality, it's usually the first case. Yes, but there are different ways to do that. Depends on how many memories or how many space you're able to access. If it's like super small chip with super limited, then it's possible they do the second way. But I think most of them is this first way. Yeah. Any other questions? Okay. Yeah, and then when you're exiting a subroutine, basically you will goes to basically the PC or program counters will be changed to the value that's previously stored instead of the LR, the link register. Yes.
So in the subroutine, when you update like register values in there and you exit the subroutine, are those values still like present, or what happens to the subroutine?
What happened when you leave the subroutine? That's a very good question. So we're gonna talk a little bit more about it, but give you a little preview. Basically, before they execute the subroutine, whatever useful value inside the register got pushed into stack, and then after they exit and then before they execute the previous functions, they pop those things back to the register. Yeah. Okay. Any other questions? All good? Yes. Where does it get updated to the return address? It's basically at the BX label or branch exit in this case, I think. So when that happens, it goes. Do you see like after that it give a address of LR? So basically give the value of the whatever address stored in LR to be its next step, which means it's kind of like a branching, but it branches instead of to like another label or to another, it branches to a register value, which is a memory value that's stored for whatever you came from, if that makes sense. So that the PC, the program counter, will know what's the next step is, that address, which goes back to where it left off. Yes? Which register? I think it's the register 14. Yeah, it's, yeah. What's the point of which one? NP? Oh, N program? That's a good question. I'm actually not sure. That's a good question. I will double check on that. I think it's usually for like safety reasons or like to have things matched up. I think it's just an ending label in case something went wrong. I think similar things happens sometimes you put like a deadlock or dead loop inside of these assembly, so that just in case, because embedded system runs all the time, right? if something happened, something became wrong, you don't want to accidentally trigger some other hardware-related process and destroy some hardware. So it basically stuck itself in the loop. I think for this one, it's pretty much the same as well. It's kind of like, I will double check on that, but I think my understanding that it feels pretty much like the exit function or like exit function you put inside of a while one after the while one loop that it never got to, but you put it there so that it's you always put there. That's my understanding, but I will double check on that. Okay, any other questions? Sounds, okay, great. Let's do a quick walkthrough of this SSQ or single sequence execution based on what we just learned. Like a quick demonstration, I guess. So first, this is like an example of basically doing like a R1 squared plus R0 squared, and then updated that into the R2. Then this is, on the left, is the, the assembly code for that. So first, and the function is called SSQ in this case. Basically, it takes two of the argument, x and y, and then the first argument goes to the R0, and the second one goes to R1. And then basically it multiply itself to itself, and then store it in R2, and the other one stored in R3, and then they add together to update the register 2, and then move whatever value there to the register 0. And why is that? Why do we have to do that move at just before the exit branch? Yes?
So I have a question, but I also know the answer.
Okay.
R0 is like the return source of return value.
That is correct.
But I'm a little curious if like R0 stores X, like would you ever need to, I guess, like that is a value, like when you call a function, if it's passed, for example, by reference, then how would you sort of retrieve that value if you sort of overwritten it with the return value?
How would you retrieve that value? I think after you reach the return that here, you go back to the previous function, right? Yeah. That X value is no longer needed for any of the process later on. After this function, after the subroutine finishes, the argument of this subroutine is no longer have values.
What if it's like passed by reference though? Like it's still
passed by reference, you mean like a memory address or?
Like if it's, you have a variable X and then you pass it by reference to here.
Oh, I see. So at this level, these things are going to be handled by the two chains automatically, so you don't have to worry too much about those. Okay. The references and stuff, that should be, at this level, it's already, all those references, it's being handled before so that we can save more. You can think about it, it's like saving more space for the code, or like more code efficient when you're at this assembly level. Any other questions? Why we what?
The value of the 12 R0 value. Let me choose R2 instead of directly using like R0.
Why are we choosing R2? I think that's a good question. I think so. You will see a lot of the lower registers from the R0 to R3 are heavily used because we don't have to preserve them or anything. And then which register is actually assigned to, that's a little bit depends on the two chain, like the compiler itself. How it's, sometimes it could be randomly assigned, sometimes depends on just some other variables. But usually they're trying to optimize the usage of the lower registers for that. That's a good point, but I don't think I recall I see any like register that does the same. Basically, you have three arguments that all from the same register. That's a good question. I should check. I will check on why that's not the case, but I think it's probably some design choices that usually don't use that format. It's usually, I think, mostly I see it's basically, especially one itself to.
Yeah, or if it's related to the like code, or by how if we just return like the 12x and the 12y directly, where it be like R0 instead of R.
Honestly, I think it's probably going to still be the same assembly code because the compiler actually is pretty good at doing those optimizations before. So if you say, like if you imagine if you're doing like a CS class and then two of your classmates have very, very, very different looking code, but it essentially does the same thing, in the end, in the assembly code, chances are they're very, very similar. It might have some different registers assigned just for whatever reason, but usually what the logic there is pretty similar. So for example, if you write like a super inefficient for loop, the compiler will optimize for you, usually, unless you did it like super bad. Okay, cool. We good to move on from this slide? I will check on that question. I think it's usually just randomly assigned or however default value they use. Once they use up the first two, they pop the third one. I think it's like that, but I will double check on that. Oh, yes. We don't have to what? Sorry.
We don't have to do calling save or calling save by hand.
When you're writing C code, you don't have to. But when you're writing assembly, which you might or might not do during the class, you have to make sure that things are proper. Yeah.
So why is R0 the return register?
That's just being defined. So the R0, it's always use R0 first, and then if it needed more, it used the R1 as well. If one R0 is not enough, it uses R1 as well to give you 64. If anything more than that, I believe they will use some. You return. Yeah, it's almost always R0.
So would R0 still be 3 after the function returns, or that the actual register R0 will be updated after we exit the function?
It will be updated, and then at that first step, because chances are you're going to need that R0, right? So for example, here, I assume you're referring to this one, right? Yeah. So that will be the value that's being returned by the subroutine. Then they use that value to do the next process. Okay, let's move on to the next slide. All right, how about this? Another example here. So basically we have a, what's actually happened on like the register level. So at the first move, it's the same code, just we're looking at it from like a register level rather than from previously like from a, just more clear. So basically the program counter currently goes to that memory address that points to the move 3 into the register 0. So the register 0 got updated to 3, and then it put 4 inside. This is inside of the subroutine. And then it put 4 inside of the register 1, and then it goes to the branch to the label SSQ, and then it moved the it basically puts the input, which is the input argument, which is the R0, and put that into R2. So I'll put that in R2. Oh, actually, yeah. I think for that reason, because currently the R1 and R2 might be occupied. But anyway, so next it does the another multiply and then store the value of the R1 times R1 into the R3, which here, and then it goes to add them together, the programming counter, and then it updates the value on the R0 and exit. And this is what magic happens. They swap the program counter to the previously stored linked register. So that it knows where the previous, it go back to the previous address of the next instruction. And then the program ends. Is that clear? Or, yeah?
It's not quite confused. Why are we like, so we're at VO SSQ, right? But then we're still seeing the address after.
Sorry, can I try one more time?
Like, you know how we're doing the instruction by saving it to PC?
Oh,
We like save the address into LR.
you're referring to here? So
Yeah.
you save that, and then what?
And then like the next slide, we essentially like add what the address of the next instruction is basically saved to LR. It's like lines. Like why are we doing that? That's a really good to like the sub.
So basically, okay, let me explain it a little bit more. So here is where the current instruction at, right? And then it tells us to branch into another subroutine. So we're gonna have to hold our position of where we currently are and also plus 4 to it, because that's what the next instruction is gonna be for once we come back, right? So the link register actually stores that value and then plus 4. And that jumps to the SSQ label on the programming counter. I think, so are you referring to like they're very close to each other? That, like why are we?
Like wondering why we're saving the address into LR of the next instruction instead of just going to like SSQ. That's interesting.
Yeah. Oh, yeah. Because we don't know where we go back to.
Oh.
Yeah. That's the reason. So like here, when we exit, it goes back to the link register and then go back to there. Yeah. Good call. Okay. So in reality, like basically all the program counter always incremented by 4. You will notice that in an example on the right, sometimes it increments by 4, sometimes it increments by 2. That's basically for because it's 16-bit or 32-bit instructions, and that's essentially just trying to make it easier for us to understand. But in reality, it's always 4-byte, which is 32-bit instruction. And then they kind of determines, as we discussed before, a specific bits inside of that instruction to determine whether it's a 16 or 32 instruction set. And the least significant bit of the LR is always 1. This is their internal label for, if it's using like a Cortex-M or, if it's using like the processor mode ARM or thumb. In our case, it's thumb or thumb 2. So it's always going to be 1. You don't have to, well, it's good to know, but we're not going to test you on this. And we're going to next move into stacks. Everyone good with the link register so far? Okay, perfect. So what this program does, it basically move the value into the register 4, write the value of 100 to the register 4, and then it branches to a foo function. And inside of this foo function, it does it put another value to the register 4, which is 10, and then go back to a link register. And if you don't do it well, then once you go back to the previous routine or function, the register 4 value is already changed, right? I think one of you guys mentioned, like, how do we deal with it? So this is the part we were going to explain how the program, how the compilers, tool chains, etc., how we're doing these things for the ABI. So basically, simply put, right after we enter the program, we will push the register 4 to the stack. So we preserve that data, and then at the end, right before we jump outside of the subroutine, we put that data back, and then goes back to the previous routine. And the reason we did this for register 4 is because, as you remember, hopefully, the 0 to 3 are basically free land. Everyone can do anything there, so nobody actually preserve anything there. But from the 4 to a little bit later, those things needs to be preserved and handled properly. So So how exactly is that being done? So there's a push function. Basically, it pushes data into the stack, and the SP or stack pointer tracks the location of where they currently at. And then another interesting thing is, or the thing you should know is that when you're trying to push multiple registers, it doesn't have a like the order you put them in does not affect how they actually got put in. So when you do these three things are essentially going to be stored the same inside of the stack. And then it's always going to be sorted by the name and the lowest numbered register. So the lowest numbered register is being stored last and popped first when you need them. Good? Which is, of course, because R0 is most used for like return values. It's for like the convenience. Yes? It's called what? Is that a sorry, we moved down from the Callie save to this is for the. This one?
Yeah, so you're pushing or pushing the server because you're using SVM instead of the stuff
Sorry, what do you mean by Callie save? Like Callie, Callie, yeah. It's this one is because the Callie preserved the values and then put it back after the execution of the subroutine, so that they did it properly. Yes. And then the pop again, just basically changing the stack pointer location, and then it pops out data from the stack. And again, this it's not in particularly any orders. It's always sorted by name and the lowest number registers. So all of these trees are essentially the same equivalent. And just to put it more visually, this is a stack here, and then that's the SP stack pointer. And then when we have that push command happening, this is what happens. It basically got pushed down, and then the SP always tracks the top of the, track where the current stack is. And then whenever it needs to be popped out, it pops out by just increasing the memory address of the stack pointer, so that they got popped back to the register. And notice that we actually didn't delete any of the data there inside of the stack. It's basically kind of being like invalidated. So because it's actually what happened in most of the memory as well. When you delete something, you're not really delete it on like a bit level. It's basically where that the pointer points to. That space became like free space for overwriting. So that's how we're able to get hard drive recovered things like that. So if you want to ever safely delete anything, delete it up, fill it with the hard drive, delete it up again, and then fill with arbitrary stuff. Do it a few times, then that's actually been deleted. So let's take a look at this example here. Basically, okay. Yep, so we go to the branch, and then the link register remembers what's the next instruction, which is here. And then before right after we enter in the substrate, we put whatever the previous needed data inside of the stack. And then after we exit, we push it again. The reason here we push the things into the stack rather than just put it into the link register is because we actually having a little bit more complicated. So we have a few more subroutines. So in this case, one link register is not going to be enough. Like remember we previously mentioned, if you need more space, you just put it in the stack. So in this case, because we have multiple layers of subroutine, and then when we go back and then back and back, the multi-layers, they have to have another additional space to store all these previous addresses, which one link register is not enough. So they're going to push that into the stack also. Yeah.
If you have like 100 variables and only the most recent like 10 or whatever can be stored in registers, how do you access one that's sort of been buried down in stack?
Yeah, similar things on the like when you're trying to, like the arguments that called through the subroutine. So if you need more space, if the forward register is not enough, you just give it an address, and that address points to the memory where it stores more stuff for the arguments. Cool. All good so far? Safe to move on? Okay. And this is just a little, I guess, more very similar example here. So basically, here the first branch goes to the quad, and then inside of the quad, later on at the end, it goes back to the main, right? But in between, it goes to another function called SQ, and then SQ go back to the previous, and then it goes again. So just a bunch of in and out, and then before they go back to the main. So, which is, we will show this in more details on how exactly are these registers are updated with the, on top of that, this green part, like the green arrow points to that location. That's basically where the stack pointer is currently pointed into. It's part of the memory, but currently it's just a different part of the memory. So yeah. So currently the stack pointer points at the 2000200, and then the PC, the program counter, which comes at the move, which is this one. So basically put the value 2 inside of the register 0, which is there, and then it branches to the next subroutine, which is the quad. So before it does that, it basically put the current program counter and then add the 4 and store that in the link register. It's part with the previous version. Hope that's clear. And then it goes to push that again because it's going to be later used to jump in between functions. So first, it put that the link register address into the stack, and the stack moves down 1, so because they have 1 value there already. And then the program count goes to the next one, which jumps to another SQ, and then which links to the previous link register. We basically put that address plus 4 and then put it in the link register again. And then next we do the multiple execution, which is not too important here, whatever it does. So the program finishes whatever it does, and then a branch exit to the previous subroutine. And that triggered a swap between the link register. So it knows to go back to there, and then it does it again because it branches it again to a different function. So that got put into the link register again, and then the program counter got updated to whatever that branches is to, and then when it exits, it does the swap with the previous link register, and then it pops again for the stored previous linked register value inside of the memory. The reason for that is at that point we have to go way back. So we have to get whatever that's previously stored back to our program counter, or first back to the link register, and then go give it back to the PC, like the program counter, and then swap that, and then goes to the end. Am I going this through too fast, or you guys kind of get the idea? Whenever you have like multiple layers, you have to store the previous ones inside of the stack and then pop it back in like a good order. Yes. Sorry. Okay, so we actually swapped a few times. Which exact swap you're not sure? This one or the previous one? Wait, sorry, what was your question again? Like, why are we doing the swaps, or? Oh, yeah, sorry. That's a good, so it's pretty much just put the value into the PC. We didn't really swap anything. So sorry, my bad. I should choose words better. So basically, we just write the value from the linked register and then to the program counter, so that it knows what's the next instructions that's supposed to go to. Any other questions? Is this? Yes. You mean this step, or? Yeah.
So if we want to push and pop multiple registers, and the stack center always implement after it moves or pop, how can we come back to the first register?
How does it come back to? So they push it in an order. Imagine you call the first main function, right? And you push something into it, it's there. And then you, into a subroutine, you push a bunch of other things in the same, in the order of the register, basically, from the lowest register got later popped up the first. And then, so they because we are doing like essentially, in this case, in the assembly case, we're doing things linearly, and then when we exit back, we also exit one at a time. So it's pretty much whenever you exit back to the previous function, whatever popped out of the stack is always going to be that's being stored the last, which is what you used in the previous function. Does that make sense? So that like the order, although within each of the push doesn't matter. It's not ordered. It's just like a default ordering, but the groups of things that's put together inside of the stack, it's pretty much in order that when we pop them, it's going to be the correct order of going back linearly.
For example, if we want to push registers to the stack, so the stack pointer will first come to the first register, the push to the stack, and then push the second register to the stack. And then if we want to pop them back, the stack pointer will come back to the first register, or not?
Oh, come back to the first, and then yeah. And then because it's being, and then when they push in, it's always the smallest number of the register, like is on the top, which, yeah. Any other questions? Or is this example look solid to you? Yes.
Then say push R1, then push R2, then I want to pop R2 first. The stack would already pointing at R2, right? The stack right?
You'll be pointing at R1. You'll be popping R1.
So, but why do I necessarily have to pop R1 before R2?
Why do we have to do that? It's kind of a set of the rules they did, and I believe they usually just, in this particular case, they usually pop up in groups instead of just popping up one. So because like whenever you exit a subroutine, all the previous register value have to be restored, basically. So they're doing it as a, you can imagine every time you go to a new function or like go back to the previous function, you can almost think the entire register value, except for the special ones and the R0 to R3, they all got updated. You can kind of think of it like that.
Kind of like whole stack with that specific subroutine.
They all, yeah, they just got popped together. Yeah, and you should not using any of the previous values that's not being passed through a argument into a new function. If you think about that, like when you write the program, all the information you needed for this function should already be included inside the argument, which got, it already have the R0 to R3 to handle that. So yes, cool. Any other questions? We can probably take one more question. Otherwise, you can come down and ask me in person. Okay, perfect. So quick recap, you can read it together. Okay, and happy Friday.